Hello everyone, we are ready to begin Module 10, which has to do with reflection of light. We've talked a little bit about the properties of light, and now we are going to get into the optics and the behavior of light as it is interacting with reflective and transmissive media. So in order to discuss geometric optics, one thing that we want to do as a preliminary thing is define what we mean by a ray of light. So you can imagine a light source giving off electromagnetic radiation that propagates around and dissipates around it. So one thing that might be useful to think of is this idea of wave fronts to this electromagnetic wave. The wave fronts you could think of them as the peak, for example, of the electric field as the light is propagating away from the source. The rays then, what we're calling the light rays, are basically these sort of imaginary lines emanating from the source in the direction that the wave fronts are propagating. And locally speaking, they're going to be at right angles to each one of these wave fronts. So you could imagine that when you get far enough from the source, right here, they're sort of curved, right, to reflect the fact that the electromagnetic radiation is spreading out in a spherically symmetric way. But you could imagine that when you get far enough away from a wave source, this curvature is going to dissipate and give way to something which is essentially like parallel lines. Of course, they're not exactly parallel, but it's a close enough approximation, and we would call these plane wave fronts. And then the light rays that we're talking about in this model are essentially perpendicular lines in the direction that the wave travels. Okay, these light rays are going to be extremely useful as we analyze different geometric optics. In today's lecture, we're only going to introduce reflection, and we will do more examples with reflection in the next lecture, and then we'll move on to refraction. So what am I even talking about? If you're using this ray model, you can imagine a ray of light coming in and striking some boundary between one kind of material and another. Now, some of that light is going to be reflected off of that boundary, while other amounts of it will be transmitted through the boundary in most cases. And so we're going to talk about this transmitted ray in future lectures. Today we're going to focus only on the reflected ray. The reflected ray and transmitted ray are actually, though, happening usually simultaneously. We're just looking at each one individually first. So, as I said, focusing on reflection only for today. So there is a law that we call the law of reflection, which describes the way in which a reflected ray of light travels. Essentially, if you imagine a dotted line which is perpendicular to the surface of whatever boundary this is from one material to another, then the angle that the incident ray makes with this perpendicular, sometimes called a normal, is going to be equal to the angle between the same perpendicular and where the reflected ray's direction goes. So theta incident equals theta reflected. That is the law of reflection. It seems very simplistic, but let's look at how this is applied to some situations. So one thing that you're probably familiar with is the experience of looking in a mirror. And so if you are seeing if there's some object, say just beneath you, it's light coming from this object bounces off of the plane mirror and to your eyes. What that does is that it tricks your eye into thinking that the light, if I just follow a straight line path, is coming from behind the mirror. This is why small children get confused as to what's behind the mirror. It's really just a trick of the eye. Is there an actual thing there? No. Is there an actual image there? In other words, could I put a sheet of paper there and project some image that reflects this image if I place it at this location? No. So this is something that we would call a virtual image. Now there is such a thing as a real image. A real image is where the light is actually converging to a point where if I placed some sort of a paper or projective screen, I could actually project that image onto it. So let's take a look at how that might occur. So one way I can actually hope to reflect the light in a way so as to produce a real image is to curve the mirror. And the simplest model for this is a spherical mirror. A spherical mirror is one in which you could think about it as being part of a sphere. Okay, so the reflective surface could be on the outside of this imaginary sphere or on the inside of this imaginary sphere. If it's on the outside, we would call it convex. If it's on the inside, we would call it concave. There are a couple other pieces of terminology that you'll need to know in order to discuss this further. The first is the center of curvature. So although the spherical mirror generally doesn't make up an entire sphere, I could imagine placing it around a sphere, and the center of that sphere would be the center of the curvature. Another term you sometimes hear is the radius of curvature. And as the name implies here, this would be the distance, the radius of this sphere from the center of curvature out to the end. And by the way, if I center each of these spherical mirror portions, then draw a line, a diameter through this sphere, this is what I would call the principal axis. Okay, so all of those terminologies are going to come up in the next few slides. So what happens then if I have a concave mirror is that if I imagine this ray of light model where I have parallel rays coming in, they are each going to obey the law of reflection at the location that they strike the mirror. And if you imagine then a little tangent surface here, and here is my normal here, then this angle of incidence is going to equal this angle of reflected angle. Okay, and then if I do the same thing with this next ray of light, and I imagine another little tangent line here, and I could create another normal here, and I would find that the angle of incidence equals the angle of reflection there. And I could go all the way around the concave surface and do that, and as I do that and I follow where each of those paths take me, I will find that all of these rays ultimately converge at this point here, which I will call the focus. And it turns out that this focus is going to be half of the radius of curvature. That is half the distance to the center of curvature. Okay, now what about a convex mirror? If I do the same thing and I have these parallel rays coming in and being reflected back off as per the law of reflection, again, if I draw a little tangent here and I draw a normal to that, and I use the incident angle equal to the reflected angle, then I do that all the way around just as I did for the concave mirror, and I will find that these reflected rays are not going to be able to converge at all. They're going off in very different directions. However, just the same way I had the plane mirror and my eye sort of imagines this being behind the mirror, I could imagine that all of these things that appear to be going in different directions now emanated from a singular point on the other side of this curved mirror that I will now call the focus. And this focus is also located half of the radius of curvature away from this center of the convex mirror. We, as a convention, give this a minus sign to reflect the fact, no pun intended, that it is actually behind, quote unquote, behind the mirror, and it is a virtual image rather than in the case of a concave mirror where I have a real image that would form at this focus. Okay, so in order to actually see how images form, we want to follow a technique that we call ray tracing. And in order to use ray tracing, you have to go back to this, get rid of this idea of the parallel lines, rays of light for a second, because we're going to place an object close enough that the rays are going to kind of go off in many different directions. However, if we just trace 3 possibilities, it will help guide our eye to see where an image is going to form and some properties about that image. So let's walk through that process. Let's imagine first that we have a concave mirror and we place an object like this and it's sitting upright as is being depicted here. The first ray that I'm going to draw for my ray tracing diagram is going to come in parallel to the principal axis. And this is actually like the parallel picture that we talked about before, so I already know that once it's reflected, it has to go through this focus. I'm just going to continue that line further until I get all the way over here. The second step is to kind of do the reverse of the first step, where I'm going to imagine a ray of light that comes through this focus. But by analogy, I know that whatever happened here that caused this incident angle to equal that reflected angle and end up with something parallel and then going through the focus, if I kind of think backwards about it, I can conclude that the reflected angle ought to also be parallel to the axis, principal axis, and come out like this. And again, I could also think about a tangent line here at this point, a normal, and make this angle of incidence equal to that angle of reflection if I'm not exactly sure how that orientation should go. Finally, I'm going to draw a third line, and this third line is one in which the ray will come in such a way that the angle of incidence is essentially 0 with respect to the normal. Therefore, the reflected light ray is just going to retrace the same path. In other words, this is a right angle. Whoops, let's make that a little clearer. This is a right angle here, as is this. Okay, they're both, the angle of incidence and the angle of reflection are 0 degrees off of the normal. So it just bounces right back in the direction that it came. And if I follow all of those rays past the center of curvature and on to this region over here, I will find that they all converge here. Since they all emanated from the tip of this arrow here, then where they all converge has to correspond to the tip of an arrow here. Now I could do the same thing for each point in the arrow, and I could create a ray tracing diagram for each point of the arrow, and I could imagine some focus here for that part of the arrow and some focus down here for lower down on the arrow and so on. But once I know where the tip of the arrow is, then I can reason through exactly what's going to happen. If that's the tip of the arrow, then I know, number one, that my arrow must be, my object, my image, must be upside down. Okay? Also, notice that it is further away from the principal axis than the tip of this original arrow of the object. That means that my image is going to be magnified. Okay, and then I could imagine doing the taking that object instead and placing it further away. And if I go through the same exercise, I'd encourage you to go through steps 1, 2, and 3 on your own and conclude that the image that is formed, again, is upside down with respect to the original object, but it is now smaller than the original object was. In both cases, though, you end up with an upside down image, and this is why, for example, when we look inside the bowl of a spoon, we'll see our reflection inverted from how we're actually looking in it, our faces looking like it's upside down. Okay, and so what we've achieved then is the formation of a real image, albeit upside down. We can either magnify it or make it smaller depending on where we place our object, but it is a real image. So the question is, can I create a virtual image with a concave mirror? I showed you how I could do that with a convex mirror. The answer is yes, I can also create a virtual image with a concave mirror. If I place the object so close that it is inside the focus of the concave mirror, then when I go through the ray tracing steps, number one being to draw the line parallel to the axis and then through the focus. Number two, one through one through where the focus ought to be, but I guess that's really kind of hard to define because you're inside the focus. But essentially draw it in such a way that when it comes out, it will actually be parallel to the principal axis. And the third one, so that it bounces back onto itself. And I will see that these rays are not actually going to converge at all. But if I continue them on the back side of the mirror as dotted lines, I can see that they do appear to emanate from a single point, which I will now take to be the tip of my virtual image since they came from the tip of my object. Okay, it's behind the mirror, it's not a real image, I can't place a screen there and project it, but it is a virtual image, and notice that it is taller than the object was originally. Also notice that it is right side up. It is not upside down. So an example of a concave mirror that produces a virtual image which is magnified and right side up, those of you who are familiar with a makeup mirror have probably experienced this kind of magnification in your makeup mirror. Now for a convex mirror, I can go through the same ray tracing process, drawing my first line parallel to the principal axis, following the law of reflection to see where it bounces off, drawing a second ray so that it bounces off at an angle so that it bounces off parallel to the principal axis, and the third ray so that it is perpendicular to the surface at that point and will bounce back onto itself. And with this convex mirror, you will see that again, these three rays of light that are reflected are not going to hope to converge. However, again, if I trace back where they appear to be emanating from, I can reason through that I should have a virtual image on the other side of the spoon. So I said spoon already, but any kind of convex mirror in which it is right side up and smaller. And I said spoon because I've given you this example here of a convex mirror in which you take the spoon and you flip it the other direction and you can see yourself right side up. Okay, and so this leads me to what I'm calling for now the mirror equation, but really it's going to also be the thin lens equation when we start talking about refraction and thin lenses. And so as it applies to mirrors, the things you need to keep in mind are, number one, anytime you're utilizing this equation, just like when we were adding resistors in parallel, you need to be careful when you're adding 1 over something so that you are adding appropriately and not combining unlike denominators. Second, with the mirror equation, you want to make sure you follow the sign conventions that are listed here in this chart. So if you have a concave mirror, your focal length is going to be a positive value. If you have a convex mirror, you want to give that a minus sign. DO stands for the distance to the object, so that's where the object is located with respect to the mirror, and it's going to be positive if it's in front of the mirror. Generally speaking, it's pretty much always going to be positive. We don't tend to put things behind the mirror because that doesn't really make any sense. And then whenever the image is produced, you'll find that you get a for DI, the distance to the image, a positive value if you get a real image in front of the mirror, and a negative value if you get a virtual image behind the mirror. Finally, we talked about the fact that some images appear larger than the object, some images appear smaller than the object. So that is determined based on this equation here, which is for the magnification. If the magnification is a number that is greater than 1, then it is going to end up being larger. If it, well, I should say the absolute value being greater than 1 means it's larger. If the absolute value is smaller than 1, then it will be smaller than the object. And if you get a plus sign, then this is a right side up object or upright object. And if you get a negative value for your magnification, this is an inverted or upside down object. In the next lecture, we'll talk about some examples and we'll make use of this mirror equation. Thanks.